Good morning to MTH129 online meeting. So we're just starting our meeting today, just talking about um, the first assignment, which has been marked and gone back. So the first two questions, which are about sets and logic, most we've done pretty well. If you've got any questions about it, you can ask offline to me, that's okay. The ones that were done the least well were the two proof questions. So at the end of my lecture on Monday, I did the induction question and I started the proof by contradiction, but I didn't record properly. So I'm just going to cover it now. And so you got any feedback? The induction question wasn't supposed to be horrible. It's supposed to be one of the what's unusual about it is that the series is going down rather than up, which makes sense to the particular application of a selection sort. Anyway, so let's just have a go at this contradiction question. So the question is, prove by contradiction if, and when you say if, the two things after the if, or things after the if here, are the premises, as I call it. So our starting points. So prove that if n is an integer and n squared is even, then we have a conclusion that n is even. And being able to do a proof sort of question, it's important to be able to tell what the premises and the conclusion are. So essentially what we have here is the premises imply the conclusion as a corresponding logical statement, if you want to think that way. Now, the way to prove things, you can go directly from premise to conclusion, which is what we've done lots of times. But a convenient, sometimes it's good to be able to do proofs going backwards. And one of them is to do a proof by contradiction, what this one strongly encourages you to do. And so for proof by contradiction, you start by assuming the conclusion is false. So I'm going to identify if the conclusion is false or not. You really need to be able to know what the premises of conclusions are. So conclusion is n is even. So if the conclusion is false, then n is the opposite, is odd. And it's good just to tell people what you're trying to do. So you know what you're trying to do, but it's good to tell people. So assume n is odd, aiming for a contradiction. So when you write it down like this, it tells people, one, you've got the result at the top, which you're trying to prove, so they can see, oh, there's the premises, you're just taking them for granted. And you, by saying aiming for a contradiction, you're telling people what kind of method proof you're doing, so people can understand what you're trying to do. Then it's good to steer in your mind to know what you're trying to do. So you do a bunch of things in the middle, and you're trying to get that contradiction. So you're trying to get things which are always false. So just reminding, a contradiction something is always false. So you can't get a contradiction by showing one counterexample. You have to always show there's a falsehood. So if you think what you've got, we know n is an integer, which sort of got to take for granted. N squared is even, and n is odd. So really, the premise is all about n squared, so we really need to consider that. So we want to somehow consider n squared. And so I go, well, no, n is odd. I want to try to get in a form I can sub into n squared. So, so because n is odd, n must be equal to, say, 2k plus 1, where k is an integer. And we want to plug in n squared. That's what our premise was about. It's the only thing we have, really. That gives you 2k plus 1 squared. And you can expand that perfect square. So if you're not quite familiar with algebra, writing some of these common rules doesn't go astray. And then you can factorize the 2 out here. And why would I do that is because I want to know if n squared is even or not. and I'm looking for the contradiction, so I'm guessing it's probably not. And so you can see you got an even number plus an even plus an odd. That's going to give you something odd. So I just want to make it very clear it's odd. And the way of making something clearly odd is 2 times by something plus 1, essentially. Um, and so that tells me straight away that n squared is odd. And the reason real in this sort of format is because 2 scape this thing in the middle, 2k squared plus 2k is an integer. So in terms of marking it, so what I told the marker, I didn't actually mark these things, but what I told the marker is this sort of middle step, as long as they made sense, essentially what we're looking for. And you can see that my instructions of the marker are in the solutions too, so you can see them there. Pretty much, you just had to go n squared, plug in the fact it's odd, and you've got to realize n squared is odd. And you've got to justify it somehow or other. There's lots of ways of doing it. Now you can see we've got n squared's even is our premise, but we've just concluded n squared is odd. So this contradicts n squared is even. And then that gets the contradiction effectively. So it's good just to make it clear. So we have a contradiction. And so the assumption we made is false. So the assumption is n is odd. So therefore, n is actually even, which is actually what the conclusion we're trying to draw at the beginning of it all in the first place. So the sort of things I'm looking for is I'm looking for the structure. So the structure is assuming the conclusion's false, aiming for a contradiction, getting that contradiction. So a bunch of steps, getting a contradiction, and a conclusion at the end. That's sort of the basic structure I'm looking for a proof by contradiction. Now, this you could have proved using a contrapositive idea as well. So in the exam, there's proof questions of various descriptions in the exam. So I've decided to make most of the proof questions a bit more open-ended, so you can choose what you want to do. But some choices are much more clear than others. So I'll give you hints though where necessary. So that's just enough about assignment 1. So if people got other questions about it, you can ask at other points in time. That's okay. So what I wanted to do today was looking at probability. So roughly, probability is equal to the chance something happens, and you know that, and you can write them as fractions or decimals or percentages, which are all interchangeable really. For your assignment 2, the online assignment, the few probability questions really require you to actually type them as decimals, so the computer can mark them. In your exam, I'll accept more forms, any of them essentially that's equivalent. In reality, often it's good to understand them decimals or percentages. They're easier to talk with. The way to work out probability in practice is there's different techniques, but essentially all boil down to it's the number of ways of getting something in particular, some special case, we'll call E for short. So getting some special event divided by the total number of ways. So the number of outcomes in this particular instance you're interested in divided by all the possible outcomes you can ever consider. That's the basic way of doing probability, essentially. And that's this sort of idea of probability is the frequentist approach, or the using formulas. So the formulaic approach. You can do probably different sorts of ways. So Bayesian stats is a bit different to that, which is certainly useful in computer science. That's a way of using probability to talk about how much you believe certain things to be true, etc. And in order to understand Bayesian stats, you have to understand this one first. So if you want to go down that line later on, really useful for predictions. Say in a game, knowing where being to track stuff, that's pretty useful. But anyway, back to probability. So Um, let's start with some um, simple questions to begin with. Um, so this is from the exercise sheet that I've been doing for the internal students. Um, and just starting simple. So um, we've got an integer. It's picked randomly. All of them equally likely. 1 up to 10. So what's the probability that it's divisible by 3? Um, so let's put you on the spot. Dylan, do you know how to do that question? So essentially it boils down to how many different ways they are getting a number divisible by 3 and divided by the total number of ways they're getting it. And there's 3 numbers out of the 10 possible, so probably 3/10. So exactly right. A prime number. So what are the possible? So again, to answer these questions, you have to have in your mind how many of them are. So what are the prime numbers? Do you remember what a prime number is? So a prime number is a number which is divisible by itself and 1, and that's it. No other things at all. Um, um, so 1 is special, so 1's not a prime. So it's called a unit. That's the other things. Um, and so essentially my question is, what's the probability of getting a prime? So the primes are 2, 3, 5, and 7. So there's only 4 out of 10. 4 different, probably 4 out of 10 for getting primes. They're all different primes. 1 is special. It's called a unit. So numbers are either primes, units, and not very many of them, or a composite. So all the other numbers, 4, 6, 8, 10, and 9. I forgot one. The other 5 numbers would be composite. So the probability of a composite number would be 5 out of 10. What about this last one? What's the probability of getting a number greater than 20? 0. That's right. So there's no way of getting a number greater than 20, so that it's impossible. So probability of 0 means it's impossible, essentially. So that's just a simple one, just looking at the basic idea. So now we get slightly more complicated ones. So we've got an urn, so a big jar essentially, and it contains some black balls and some red balls. And what I want to do is I want to pick some out. Oh, you there? Can you hear me again? Okay, good. Okay, don't know what happened there. So so basically we've got a big jar, which I've drawn really poorly, with 6 black balls and 3 red balls, and we also want to pull some out. And what we're going to do, we're going to pick out 3 different balls, essentially. And I want to know how many of those, and and you can get 4 different possible arrangements, either all of them red, all of them black, or 1 red, 1 2 black, 2 red, 1 black. So they're the 4 different options. What are the probabilities of all these different outcomes? So let's just do a little table up here. So we'll do the number of reds, and we'll do the probability. So you need to have all reds, which is 3, 2, 1, or 0, essentially are our cases, and we work out the probability of each of them. And so we'll do all red. first. So I want to show think of two different ways of doing this sort of approach, and talk about what's similar and what's different about the approaches, and then you can tell me what you think what you prefer. So with all red, there's two ways of sort of doing it. As in, we just at the end of the day we only care about how many red we have. So we don't really care about the order the balls have been taken out, just what's been taken out. But sometimes it might be easy to just think, well, we do have a ball that comes out first and the ball at second, bell third. So it's useful just to think about the order we take them out. So that's one way of doing it, thinking about the order, but just taking into account we still only want 3 red balls. So you take them out in order. The first ball that comes out we want to be red. There are 3 red balls in the urn, out of the 9 that are in there. So one way I think about it is for taking the first red ball, there's 3 knights or a third chance of pulling the first ball being red. And you want something else to happen. So when you got an and, it's sort of a multiplication. For the second time, the probabilities are changed. So you're going, well, there's only 2 red balls left at this point in time, and there's only 8 balls in the urn left. So it'll be 2 8s for the next red ball. And lastly, you've got 1 red ball left out of the 7 remaining. And that, if you multiply all those together, that would give you the total probability. So whatever that is, 3, 4, 12, 1 over 84, I think. So which you could understand as a decimal if you want to. It doesn't happen very often, essentially. So that's one way of working at the probability. And that's talking about an order. So we are thinking of the order the balls come out. On the other hand, we could do it differently. And the different approach is just to think about, I go, well, I don't really care about order because I'm just counting the number of balls. So you can sort of do it all by counting by combinations. And the other way of doing it is you're going, well, I've got 3 red balls. I will like to pick all 3 of them. So do you use a combination or a permutation? So if you want to pick the balls out, yep. So you got a combination, and from the 6 black balls, I would like to choose none of them. So that's a number of ways of choosing without order the number of balls we have. And then I want to divide that by the number of ways of choosing the balls at all. So I've got 6 plus 3 or 9 balls in total, and I want to choose 3 of them. So if you look at this particular probability, and if you type in your calculator, you'll get the same answer. It gives you the same thing. So as a matter of fact, 3 choose 3 is 1, 6 choose 0 is 1, and 9 choose 3 should be 84, if I've got everything right. So this second approach really is just thinking about the probability of different combinations, so different order and different things without order. This first approach really is equivalent to 3p3 or 3 factorial over 9p3. And that's thinking about different ordering. So not what proportion of the ordering satisfy having 3 red balls, essentially. And so, although they look different, they're slightly different approaches, they're both equivalent because at the end of the day, we're still counting the right number of things. We're still counting and the proportions will match up, and that's the key thing. So out of those two approaches, which do you prefer? Do you prefer the left or right? And again, it's up to you. I mean, at the end of the day, you have to do sort of things. So for small numbers, yeah, left works. So you just look at the black one. Let's look at the bottom one here. So let's look at all black numbers. So if they're all black, then it's the same sort of idea. You've got 6 choices for the black ball out of 9 times 5 out of the 8 remaining times 4 black balls remaining out of the 7 remaining to the same sort of idea. And that would give you 20 over 84, which you can simplify further if you wanted to. Different ways of getting all blacks. And as you can see here, you've got a much more likely chance of getting all blacks rather than all reds. And the reason for that is because you've got twice as many blacks as there are red balls, so it's certainly going to be much more likely to be the case. So that's the same sort of idea. And so those are both simple enough, you can do it quite readily. The harder cases to do really are these two in the middle. So the next one is C. To A, B, C, D. Done in funny order, haven't I? So for C, I really want to have 1 red and 2 black balls. And so because we're worried about, because this sort of way the counting on the left worries at order, we have to think, well, that red ball can come in first or second or third. So there's a few different orderings that are possible. As a matter of fact, there are 3 orderings. So the way to do that would be I've got 3 possible orderings. So that's the number of orderings. And for each ordering, essentially, I've got to pick the red ball. So if I picked it first, for example, I'd have 3 out of 9 to pick the red first. And then I have to multiply by, well, I got a black this time, so there's 6 black out of the 8. And then I'll pick another black ball, so there's 5 left out of the 7 remaining. So this bit here, this sort of term is, that's the number of getting a red, then 2 blacks in that particular order. And so, but there's other orders. The other order could be red in the middle or red last. And they'll all be the similar sorts of patterns. It's the same numerical value, as a matter of fact. And there's 3 different orderings we have to consider. So we really have to multiply that by 3. And so you can work what that is equal to. So it's 45, I think. So 45 out of 84. And so you could do that instead using combinations. And you're going, well, I don't really care about the order, and then you don't have to, and therefore the combinations take lots of it into account. You know, of my 3 red balls, I just want to pick one of them. That's 3 ways. Of my 6 black balls, I would like to choose 2 of them. So 6 choose 2 gives you 15. So 3 15s gives the 45. And it's still divided by the 9. Choose 3. And so the way to approach D, which is 2 red and 1 black, is similar. And so if you're doing the approach on the left, which a lot of people like you do, it's the hardest thing to remember is the fact that there's 3 possible orderings. So people often forget the 3 times factor there. Now for the A and B, the first 2, there was only 1 ordering possible, and so you didn't have to worry about it. But the harder ones you do. And so again, we'll have the term at the beginning is the one you have to worry about. So if you want to have 2 red and 1 black, there are 3 places to have the black. So there's 3 different orderings possible, and otherwise it's similar. So I've got to pick 3 out of 9 for the first red, 2 out of 8 for the second red, and then 6 choices out of 7 for the picking up a black ball at the end. And there's sort of similar 3 sort of things. And if you multiply those together, you're going to get 18, I think. So 18 on 84 different ways of picking that option. Now, if I did it properly, if I add up these 3 cases, they're all mutually exclusive and cover all options. These should add up to 1 if it works properly. So you've got 1 plus 18 is 19, plus 20 is 49, plus 45. So 39, I should say, plus 45 gives you 84. So they give you 84 and 84 gives you a total probably of 1, which is good. That's what it should always be. And so if you're doing a few cases, that's one way of doing it. And so therefore, the other way of doing D over here is just to go, well, I know the whole thing's supposed to be 1. If I add up these 3 other numbers and do 1 minus that, that should give me this last figure. And sometimes that's easier. In this case, probably not, but anyway. So what we've done here is we've produced a probability distribution, which we'll do more in next week's online meeting. But it shows you that it's much more likely to have more blacks, less reds, which is totally not surprising given the ratios in the bag that earn in the first place, etc. Okay. So next one is, what's the probability of getting a 3 of a kind in a poker hand? Now, I'm not sure how much you understand poker. So poker is 5 cards. So you got, and so it's basically, so poker is getting 5 from 52 cards. That's what a poker hand looks like, or a standard one. Of those 52, there are 4 suits, and each suit has 13, I guess you call numbers in them. And the numbers are ace, king, so ace, 2, 3, 10, jack, queen, king. So what they mean by 3 of a kind is you have 3 numbers that are the same, something like so 2, 2, 2, so 3 numbers that are the same, and they can be different suits. So big diamond, club, and heart. So that could be 3 different suits, but 3 different numbers, and the other 2 numbers have to be different from that, so they can't be any more 2s. Something like, say, a 3, diamond, and another number which is different. So let's like jack of spades. So that's an example of a 3 of a kind. So in particular, of a 3 of a kind, these other numbers on the end here can't be another 2, can't be repetition of the first ones, and they have to be different. If they're the same, it's called a full house. If there was 4 2s, it's called 4 of a kind. So we want to exclude some of those particular cases. So what we do is work out the probability of this. So what's the probability of a 3 of a kind? So this one's tricky because you have to think of the various options. Let's do the bottom first. How many different ways are there of getting picking the 5 cards for the poker hand from 52? How many different ways of doing that? Yeah. So I've got 52, choose 5. And so you're always right, the one where you're choosing from first. So that's right, that's the bottom, which your calculator knows quite happily. So it's the top we have to worry about more thoughtfully. And because we want to make these numbers different to each other, but we don't really care if the suits match or don't match, we really need to consider them differently, split them all up. So the way to do this, my recommendation, is basically just to do the numbers first and then worry about the suits. So first of all, let's pick the number. So for the 3 of a kind bit, so that number's got to be the same for the first 3 cards. So how many choices are there for picking that number? Again, it depends how much you know about cards to know the answer. So how many different choices are there for picking that number? Pardon me. To know the answer. If you don't know, just put question mark. That's okay. Yeah, so there's 13. So on the top here, there is 13 choices. And so we're going to work on the top here, we're going to write down the total number of ways of choosing 3 of a kind, essentially. And we're going to divide that by the total number of ways of getting any hand at all. So there's 13 possibilities. So that's getting the number. Well, it's in commentary. That's the number for, positions um, for position for the 3 of a kind bit. So positions 1, 2, 3, we'll give them positions 1, 2, 3. Then we need to pick the next two numbers, and we'll write suits in a little bit. So now you have to pick the number. So we want to make a choice. So now we want to pick a number for the next position and the last position as well. So this is going to be the number for position 4, and this one here is going to be the number for position 5. And we want to make sure that they're different. So what's this first one? So how many different possibilities are there for choosing this fourth card, the number for it? And again, we're not really worried about suits at this point in time. It's just the number on it. So whether it's a 3 or whatever it might be. So how many different choices are there for it? So you think there'd be 52 minus 3, and unfortunately, that doesn't quite work in this situation, and I'll explain why. Although it's a good guess. So 52 minus 3, which would give you 49, would allow that this card here be a 2 again. So it allows the 2 to crop up again. So that would allow the possibility for 4s of a kind, which we want to explicitly exclude because if you ever play poker, they don't call it a 3 of a kind, they call it something else. So if you just wanted to count all the ways of getting 3 of a kind and maybe 4 of a kind and full of house, you want to get all of them together, then you could indeed do that approach. I'll do 52 minus 3 for the last 2 cards. But because we want to be more special, we have to exclude it out. And so I was looking at just the number, and so there are 12 other numbers to choose from. So we really are ignoring suits for the moment. The 52 minus 3 allows things about all the different suits. So we really have to be more thoughtful about this. Have to be more careful, I should say, more careful. So there's only 12 choices for the numbers, and for the last card there'd be 11 choices for the number. And why 12 and then 11 is because I really want to insist that their numbers are different. And again, that is a good way of guaranteeing that we don't get a full house as they go. So that's just the numbers. We also have to worry out the suits as well. So we have to count the suits for the positions 1, 2, 3. So let's think about it. So for the first 3 bits, all the numbers are the same. So it's 2, 2, 2 every single time in this case, in the example. The suits have to be different. And the reason being is because you've only got one. Each number, there's only, for each number and suit, there's just one possible card. So I've got to pick 3 of the possible suits to represent here. So how many different ways are there of picking the 3 suits from the 4 available for these 3 cards? Any idea? Again, question mark's fine. Yeah. So I've got 4 different suits. I would like to pick or choose 3 of them to make the suits up for these cards just here. Now I want to choose suits for the other cards. So I want to choose the suit for the card 4 and the suit for card 5. And for this card here, the suit could be anything. It doesn't really impact it by anything else. So there really are there's 4 choices, or 4 choose 1, if you think of that way. And again, for the last one, we don't care what the suit is. I can have any choice at all. So 4 choices for the suit. And so something along those lines. So 13 times 12 times 11 times 4 choose 3 times 4 times 4 is the total number of ways of getting precisely a 3 of a kind. And equals whatever number that is. So just as an aside, just to link with what you were thinking, so the probability of getting 3 of a kind or 4 of a kind or full house. So looking at all these different options. Then before I answer this one, doesn't matter about the suits because you can't make a flush with a three of a kind. The answer is it does. Um, we want to make sure we count accurately. So the 52 choose 5 includes all the different options, heaps of the options, and we want to get the right proportion of them. So the answer is we do have to write the suits because we want to make sure we count this three of a kind, but also the same three of a kind which has a spade rather than a club here. And so we want to make sure we count them all so we get the right probability. So if you exclude the suits, then you'll undercount them quite considerably. You get the probability wrong. Let's just try to bundle all of them together. Just think. So we got three of a kind, four of a kind, or a full house. So we'll do three of a kind or a full house. So we'll just do one or the other. Four of a kind's a little bit trickier to try to handle all in one go. So you got to pick there's 13 choices for picking the card for the three of a kind. And you got to write the suit. So you got 4 choose 3 ways of picking the suits for the three of a kind. Then you just have to pick up some other cards to make up the numbers. And because we don't want the four of a kind, there are 52 minus 4 or 48 other cards we could pick from, and we want to pick 2 of them to make up the numbers, essentially. And we do the whole thing by 52 choose 5. So that's close to what you were thinking before. That is, I just pick the three of a kind, pick the suit to pick the number for the three of a kind, pick the suits for the three of a kind, and then just pick, 2 more cards to make up the numbers. Who cares what they really are? So the difference here in what we've done, the difference is this versus these terms here. So 12 times 11 times 4 times 4 basically really forces the 2 cards to be different. It really is forcing them to be different. Where over here, we haven't really cared if they're the same or not. And so this will count the full houses as well. And so you can also factor in trying to count the 4 of a kind as well. But that gets a little trickier potentially because you'll double count things quite easily, and so it's a bit more of a fiddle to fix it up. So it's easier to do it directly. So why I count the poker hands is one, not everyone, but lots of people are familiar enough with the poker to get the idea, and the number of ways to count them is not trivial, as you can see here. I mean, it's certainly a bit harder. Someone asked in my internal tutorial, would I ask this sort of question in the exam? And the question is, I would only ask a question like this in the exam if I could fully explain it. So not everyone, I really can't assume everyone knows what poker is, let alone deck of cards. And so I would need to explain it. If things are just getting if just getting too many words to try to explain it, I wouldn't end up asking in an exam situation. Plus this one's getting on the trickier side. So you could fall over on something really simple, understand a lot. So this is only one I would call a harder question. So just picking one last question just to give a different sense of probabilities. So just something a little different. And that is define, you can there's a nice link with probability and sets. Just trying to understand it all. So we know we've got 2 different events, A and B. We know the probability of A is half the time, 50%, 80% for B. The probability of both of them happening. So just write a few things down here. So A and B is 30%. We want to know some various probabilities based on that. I feel a useful way of sort of approaching this sort of question, which is why I want to do this one, is really to draw a Venn diagram. So I draw a rectangle. So there's a total probability of landing a rectangle of 1. So that's sort of the universal set. So that's a guaranteed. I've got two circles, A and B. And so I know I know some probabilities here. So the probability of landing in all of A is 50%. So I'll told that. And the probability of landing in all of B is 80%. And then the other thing we've been told explicitly is the probability of landing in the intersection, so A and B, is 30%. So there's three things I was given in the question. Now I got to work at some other stuff, but I reckon it's before we go to that stage is if you think about it, this sort of Venn diagram really splits up the region into four different shapes. So there's one is the intersection, the other one is sort of this Pac-Man shape over here, another Pac-Man shape over here, and the last one is everything else. Which is everything in the box, and then about on the outside, probably these two things. So that's the four different shapes it splits it up into. So it really splits the region up into four different regions. Let's work out the probability of each of them. And we'll do it, and there's formulas for it all, which you can utilize, but it's just easy using the picture, I reckon. So we know what's in the red section is 0.3. So what's the probability of landing in this green Pac-Man shape? So the total probability of being an A is 50%. The probability of being an A and B is 30%. So what do you reckon the answer is going to be for this green section here? 20%. So 0.2 or 20%. What about, and the way you did that is you just did the difference. So 0.5 minus 0.3, it's all it covers bounds to do. What about probability of being in this blue Pac-Man over here? Yeah, 50%. That's right. 0.5 or 50%. And what about in this outside region? This one over here. So what's the probability in the outside region? And yeah, I need a 0%. And the way to do that is you know that you've got 0.2 plus 0.3 plus 0.5 in the middle, which if you add them up gives you 1. And the whole box is 1, so you do 1 minus 1 gives you nothing left over. So in terms of, all right, this is 0. So the way to think about all these different regions, this outside region is not A and not B. That's the outside region. This Pac-Man over here is B, not A. This Pac-Man over here is A, not B. And the intersection, as we've already said, is A and B. There's nothing wrong with saying and rather than intersection. So that gives you that's broken the whole region down into all different situations. Now we can sort of sum them up. So the probability of A or B then is looking at our picture is you're going, well, I've got the 0.2 from the first Pac-Man plus 0.3 overlap plus my 0.5 from the other Pac-Man, and if you get that, you get a total of 1 or 100%. So that's one way of doing it. The other way of working out an OR probability is to say that's the probability of A or the probability of B minus the probability of A and B. So that's the general addition rule. And if you did that, gets all these different numbers, so 0.5 plus 0.8 minus 0.3, and the answer is the same. So they match up, but this here requires you to remember the formula, which you have cheat sheets for in a linear exam. The top one really is just all about using the picture alone. Really is, you don't have to think of formulas, you can just use the visual approach, which is why I recommend it. Other ones is what's the probability of not A? Now, uh, let's do the visual approach and then we'll do the formula approach. So the visual approach is I want to look at all regions which don't contain A, and that would be the blue Pac-Man shape is not in A, and the purple, which I'll just use black, I think. So then the purpley region on the outside also doesn't A, which is 0. So therefore, there's a 50% chance of not being an A. And again, you can see that visually. In a formula approach, which actually works really nicely, is a probability of not something is 1 minus probability of it happening, which is a simple enough formula that's probably worthwhile remembering it. And that would be 1 minus the 0.5 from earlier, which still gives you the 50%. So no change there at least. For the next two parts requested, so what's the probability of not A and not B? Well, we can see from our picture that that's going to be nothing. See, nothing is on the outside of it. And what's the probability of A and not B? And we worked that out already as being 20% or 0.2. So those ones we can read off from our picture straight away. So the last one to do is this one here, a vertical line B. So how I'd read this out, what's the probability of getting the event A given that B's already happened? So we know that B's happened. If we know B's happened, what's the probability of getting A? And we've used, this is called a conditional probability, and we've used this fact already. So for example, this 2/8 here is the probability that the second ball is red, given the first ball is red. So that really is a conditional probability. And again, we've got lots of them over here. So we've used them implicitly often, and we can do formulas directly. But if you're not, so often you can do it intuitively, but sometimes formulas are useful to have at your disposal. So in general, the formula for A given B is pretty much saying, well, I really want to work out the probability of something of this particular outcome happening divided by the total number of ways. Well, if B is happening, really that's my new total. So my new total is just the B. So the bottom should be the probability of all B's. The top should be all the ways of getting A. But I want not just A, but I know B is supposed to happen too. So the prop is all the ways of getting A when B's also happen. So the top is probability of A and B. So it really just boils down to the same trick. So that's the basic formula. And now we know that, we can sort of read off our answers. So probability of A and B, well, that's the 0.3 we can see from the picture. And probability of B, we know, is 0.8. And so therefore that's probability of 3/8 or 37.5%, or 0.375. They're all the same, of course. And in a similar way, we can work the probability of A given B is false. And that would be the probability of A and not B happening divided by the probability of B not happening. And we can read these various things off. So the probability of A and not B is just sort of this green Pac-Man shape we've worked out already. and we want to divide that the probability of not being in B, and so not being in B is either the 0.2 Pac-Man shape, or it is the sort of purpley area over here, which has got a probability of 0. And so if you do that math, so 0.2 on 0.2 gives you 1. So if we know that B hasn't happened, then it's certain that, hey, A will happen. If B has happened, well, we're not certain. There's only 37% chance that A will be happening as well. So this is the idea of conditional probabilities. And so therefore, you can see the key formulas that I've used. So these are sort of the key formulas that sort of dictate these sort of things. And they're useful by all means, but it's also useful to try to understand some things a bit more visually as well. And so a Venn diagram for simpler cases like this one can be useful. But you need to have your sort of a bag of tricks, I guess, at your disposal to work out what to do. So, any questions with that? No. Let's do. Oops. So this is the last sort of question that I want to cover. So just try to think of various things. So we've got two urns this time, and they both contain balls, but different numbers of balls. And basically, we pick a ball at random, just one ball, and we pick. And so basically, what we really do is we pick an urn at random, so equal chance, and then from that urn, we just pick a ball out. What's the probability that the ball is black? So let's just try to think about this one. So what's the probability that the ball's black? Well, first of all, we've got two sort of situations happening. You've got to pick. So either you've got urn 1 or you've got urn 2 being used. Now, these two cases are mutually exclusive, and so when you've got a probability of one or the other, when they're mutually exclusive, it just becomes a plus. So it's going to be one probability plus the other one. So the probability of getting urn 1, well, first got to pick the urn. So there's a 1 in 2 chance of picking urn 1. So I actually got to pick it in the first place. There's only half the time it happens. And then you have to multiply that by the probability of getting a black ball. So in this first one, so this is the first urn, so 3 black, 5, 3 white, 5 black. What's the probability that if you pick one ball, you'll get a black ball? Can you tell me the answer? So if you've got 5 black, 3 white, and you pick one ball, and put a question mark if you don't know, what's the probability of getting a black just from that sort of situation? Okay, so that's right. So you got 5 out of 8. So that's the probability of getting a black ball from the first urn. Or you can have black urn from urn 2. So again, there's only half the time will actually urn 2 is available. But if you do have urn 2, the probability of getting a black is, see if you can tell me the next last bit. So you've got 2 black, 4 white. So the probability of picking the black from that sort of urn is equal to, yep, so 2 from 4 or 1 out of 6. So same thing. That's what you write down. Absolutely correct. And you can, and we can work this out. So your calculator is more than happy to do it, but I'm just going to try to do it on a piece of paper. So that's equivalent to factorising half out. So that's 15 plus 8. So it's going to be 23 out of 3 16s, so 48. So something along those lines, I think the probability is. So again, calculator's happy to work it out. So the probability, therefore, of getting a black ball is 23 over 48. The probability of getting a white ball could be done in a really similar fashion, but it's just going to be easier to realise that if it's not black, it's white. And so if I just do 1 minus this number here, I'm going to get 25 out of 48. So it's slightly more likely to be a white ball than a black ball. And if so, if you think about it, you've got 7 white balls and 7 black balls in the 2 urns. You think, oh, I would have thought they'd be exactly equal, but this urn over here has got more white, and so if you ever pick this one, there's a slight stronger bias in this case. So anyway, that's the answer. So that's part A. And I've just done this one as an extra one. So let's do something a little differently. A ball is drawn and found to be white. What's the probability that was taken from the second urn? So what's the probability that we've actually come from the second urn given that the ball is white? So this is actually asking for a conditional probability. So this is one of the harder ones we're talking about. What's the probability that it comes from the second urn given that it's white? And you notice how the question's asked and how you often phrase it in English is actually to mention the condition first and then the other thing later, whereas we often write it backwards. It's easier just to write down what the situation is. So the probability of a conditional probability is both of them happening, so both getting a second urn and white, divided by the probability of getting just white. Now, probability of just white, we know that's 25 over 48. We worked that out. So I worked that out just to make it easier. So the probability of getting the second urn and white, well, there's a 1 in 2 chance of picking the second urn. And then if you want to make it white, we then multiply to get white. Well, there are 4 whites from 6, or 2/3, as you would have said before. So half times 4 and 6 would be the probability of getting both the second urn and white from it. And then you've got to try to clean it up, essentially. To simplify that fraction down. So I think you get something like 16 over 25 as a final answer. Or 64% as a percentage. So that's one of the harder questions. So really just the way to really work it out was just go, what's the probability that of second urn given white? It's just the both together divided by total probability. This last case is an example of you can use the Bayes theorem to work it out. I've done that explicitly, but so you can do more of those sorts of things. That's a sort of common technique in more advanced probability and stats, which is used in Bayesian stats, for example. But just having, so I guess in this subject, I just want you to have the introductory understanding of it all, in case you ever see it later. So that's all I wanted to cover. If you've got any other questions, fire away either now or later, since lots of people are going to be watching the recordings rather than being live. So if you're going to be later, that's okay. But please make sure you do practice. The other thing is, for your assignment, next assignment's online assignment 2, you can do all the questions now apart from the very end. So the very end is about probability distributions, and it looks like a table of probabilities essentially. So that question you can't just do yet. Well, I haven't explained everything in class yet, but everything before that you can do. And so it's worthwhile having a go, and trying them. Um, it's an assignment, really. It's not a quiz, so therefore there's no time limit. You can go in and do some questions now. As soon as you type it in, it tends to save it automatically. But if you're not quite sure, you can press the click on the save button just to be doubly sure, and then you can close it and come back to it later. Um, the only thing is once you've hit submit, that's finished. Now, if you accidentally press it, I can unlock it again. I certainly can do that. But yes, it's worthwhile just having a go, just doing a few at a time, and make sure you do practice questions from the study guide or textbook as you're going through, just to really get on top of things. Um, so just to have your full understanding. So thanks very much for being here today, Dylan. It's good to talk to somebody, and hope to see you next week. Cheers.